favorite. Just because I'm a math person, you know, give me math and we can put the formulas in. We did thermochemistry, we have our formulas. This one, I tell my kids, they get really tired of me because I tell them by the end I sound like a toddler because I'm always going, why? And did you guys grab the packets? Okay. That is where we've seen the real change in the rewrite, that when they went to the new test in 2014, they took out a lot of the math, which for a lot, and the grades went down for a lot of them. Because math is really kind of easy to memorize, and you can really crunch it out and figure it out. Now they're making you, they love the words justify, explain, justify, explain. Thankfully, we're not apes, we're not AP Environmental, and we're not bio. We don't have to use as many words, but we still have to use some words. And so for this, I don't try to say there's buzzwords or keywords, but there really are. There's some keywords they're looking for when you're talking about this. So it all comes back, think the structure of the atom. Remember we have the nucleus. We like Bohr's model for this because even though we know technically it's not correct, does Bohr's model help visualize and see what's happening? Yes. What's the charge of everything in the middle?
Neutral. Oh, it's positive.
Positive, because the protons are positive, the neutrons are neutral. Now, what again, they took away nuclear from us, which was kind of too bad because it really was interesting. Again, in physics 2, if you choose to take physics 2, you actually calculate that mass defect, because I've had kids go, why is the nucleus being held together? Because if you put a bunch of positives in there, what should they be doing? Yeah, repelling. So why is this nucleus being held together? And the answer to that is actually the mass defect. If you used Einstein's formula, E equals mc squared, if you added up all the sum of the parts of this atom, it doesn't equal the actual mass. So some of the missing mass got changed to energy. That's the energy holding the nucleus together. It's one of our basic, it's like gravity. We know it's there. We don't really know exactly how it happens. It's just a strong nuclear force. But what we care about then is the attraction then, because what's the charge of the electrons? Negative. This is what you have to talk about. So when you're talking about trends, you're talking about the attraction between the positive nucleus, the protons, and the negative electrons. That is what you should reference when you're saying why. And in fact, they love Coulomb's law, the Coulombic attraction. You talk about it in ionic compounds. Why some ionic compounds have a higher melting point or boiling point. You're going to use this when you're talking about the structure. So what does Q stand for in Coulomb's law? The charges, okay? And so the charges in this is the negative electron and the positive proton. So the stronger the charge, the stronger the force. And then what's the D stand for? The distance. And again, it's the distance between the charges, between the positive and the negative. So the stronger the force, notice it's proportional. We don't use this quantitatively. We will not calculate it. This is not on your formula chart. But they will ask you to answer in terms of Coulomb's law. So the stronger the force, the stronger the attraction, the stronger the force. But the larger the distance, what's that going to do to your force? Because if you divide by a larger number, what happens to your answer?
Becomes smaller.
It gets smaller. So when you have a larger distance, then then the force gets smaller. So anytime trends, anytime ionic compounds, Coulomb's law needs to come to mind. That's how they wanted you to answer it. They don't want you to talk about shielding. They don't want to talk about that. This is what they're going to say. So they've even started saying, in reference to the attraction between the particles. So part of this, in the unit, there is some math. And it all comes from figuring out what these electrons act like. So they based it on light. So the formulas, the math in this unit, comes from the property of light. These are on the formula charts, that wavelength times frequency is speed of light. careful in these problems. Wavelength is in meters, but a lot of times when they give you a wavelength in a problem, it is in a nanometer. They don't give you that conversion. How many nanometers in a meter?
Like
A lot.
a bunch.
Here's what I tell mine. Nano is nano. Nano is nano. So I know that there is 1 times 10 to the 9th nanometers in every meter. So nano is nano. They give you conversions in physics. They don't give them you in chemistry. They definitely don't in AP environmental. Frequency is just how often, and they give you speed of light, and I'm sorry, I think speed of light, do they give you 2.998 or is it 3.0? Use whatever they give it to. Is it 2.998? 3.0. Yeah, I have to change that, sorry. So the nice thing is they give you that formula. If you ever have to need it, it's on the formula chart. So what happened, for a while, there were like 2 groups. One group of scientists said light is a wave. I can prove it with the properties of wave properties. It diffracts, it refracts, all the things that a wave does. Light does. I can have interference. Max Planck came by and said, no, light is really a little packet of energy. And it's you can, because of the photoelectric effect, that light isn't a wave, it's traveling in little bundles of energy. So he came up with his formula that energy is Planck's constant times the frequency. So light traveling at a higher frequency will have higher energy. Now this we take into account when we start changing energy levels. The nice thing, they've taken that math out. So that's why in the formula chart, you're just going to talk about 1 photon, and 1 photon is Y and is 1. Hey, it was Einstein that brought it together and said, you know what, it's both. It's a dual wave particle light. And because of energy in, it's going to start kicking out electrons. This is how we were able to calculate ionization energy. Because if I know how much energy I put in, what's the conservation of energy say?
It can't be created or destroyed.
Can't be created or destroyed. So if I know energy in, then I can calculate energy out. And so the energy in, energy out is how they were able to determine ionization energy. So sometimes when we look at data going, how do they know this? We can't see an electron. This is some of the data that they started using. And so what happens is we can combine these two, and this is where conceptually you can look and say, well, the energy of that light is going to be inversely directed to the wavelength, but I know it's directly related to the frequency. One thing on this problem with doing these calculations, because again, they're formulas. We like formulas. You can plug them in. Remember that we're assuming this is 1, so it's 1 photon or just 1 little electron. But what if they give me an energy in mole? How many moles, how many electrons do I have, or how many photons do I have in a mole? 6.02 times 10 to the 23rd. So that's where you have to be careful. Are they talking about just the energy of a photon or energy for a mole of photons? And that's really the only tricky of this, and I think there's one that we're going to kind of focus on. But what they discovered, red light, long wavelength, didn't have enough energy, didn't kick out an electron. Green had a little higher energy, had enough to kick it out. Blue, it actually kicked it out at a greater velocity. And so that was, again, they could have the evidence to show the ionization energy. So did you guys do in pre-AP the flame test lab? And you see all the colors? Did you do that? Yeah. That was the one that my pre-APs actually like chemistry, the one day. Because you put in copper and it burns a different color. You put in sodium, it'll burn a different color. Electrons, when they're in the ground level, they're boring. When you add energy, they jump up, but they can't stay there. And so when they fall back down, that's when we see colors. Now, this also was how we proved Bohr's model, because we didn't see like a rainbow spectrum. Because before, after Thomson, when they just said electrons exist, Rutherford said the nucleus exists, but they still thought electrons could go wherever they wanted. Bohr's the one who started playing, and if they thought it could go everywhere, we should see it in a continuous spectrum. We only saw lines. That's how he said, oh, electrons can only exist at certain energy levels. So I can only see this set energy, which corresponds to this frequency, this wavelength. So a shorter energy difference gives me a lower energy light. If I get a larger energy difference between the transitions, you're going to get a higher energy light, which means you're going to get a wavelength with a shorter wavelength. So that's Joy-G Biv that we're seeing the color spectrums. Okay, these are in your packet. These were new things to the rewrite. Have you guys looked at these and see PES diagrams?
Never heard of it.
Okay, if you've never heard of them, and it's really kind of funny when they did the rewrite and they said we're going to have these PES, teachers were freaking out. Why? Because I'm a nerd and we have a Facebook group and we have messaging boards, and teachers were freaking out in the beginning. And then once we started seeing them, we're going, oh, that's it? These are actually kind of easy. Again, this is what they love showing these because it's the evidence to support, and it's all about the evidence. So what this is they're just saying, hey, we put some energy, and this right here, this blip, is showing you the energy needed to remove the electron in hydrogen. Okay, that one blip. Now compare it to the energy needed to remove electrons in helium. What do you notice difference about the group? Okay, there's two things I want you to notice. What's one thing that you notice about the height of the peak?
Helium is
Okay,
higher.
it's double in fact, right? How many electrons does hydrogen have? Hydrogen. One. How many does helium have? Two. So does that make sense that it was double? Okay. Now, look at the difference on the energy though. How much did it take to remove an electron from hydrogen? 1.31. But to remove an electron from helium, it's a little bit more. This is starting to explain the trends, and then we'll talk about the trends. But this is, again, this is how they, a lot of times they now show you trend questions. It's going to say, look at the data, look at what you're having. Okay, so look in your packet. They have a lot more, and I just didn't want to cut and paste these. It's like, it's much easier just to open these. Yikes. I hate my husband's computer. Okay. Now let's look, okay. So these are the same thing that you have. We looked at the hydrogen and the helium. Okay. So there's hydrogen and helium. Let's look at the next one. Lithium. Okay, but look at what happened to the data. I had a peak here, so this is on the next page, that had, so we had hydrogen and helium, they had the same peak. Well, now I have a peak that had the 2 electrons, but what also happened in lithium? There's a new peak. But its new peak only has 1 electron, so this is still taking into account my 2, 3 electrons. Then look it on down. What happened to beryllium? You had your first peak, and then you had another peak, this one with 2 electrons. Scroll on down. So like, we're the scientists. We're figuring out what all this is telling us. Okay, now look at what's happening. So I have boron. It had 2 electrons. 2 electrons. Then what the heck? I'm still in the second energy level, but what's starting here? Another peak.
What's the bottom?
Yeah, it's looking like they can only do 2 at a time. But let's keep looking at our data.
What does the bottom mean?
Okay, the bottom, the bottom is the energy. Okay, this is your ionization energy. They will do it in like megajoules per moles, kilojoules per mole. Typically, if you have to ever use that number, it's going to be in kilojoule per million. So that's your ionization energy. Okay, so carbon, 2 peak. So we're thinking, okay, it can only hold 2. Uh-oh, what did nitrogen just do?
3.
well, where, if we can picture the periodic table, where are we on neon now?
Double gap.
Yeah, we're at the, so if you look, we're all the way through the second period now, right, with neon. Okay, so what do you think, let's predict, what do you think is going to happen in the next row?
It's going to go back to period.
We're going to go and look at what happened. It went back and made a new peak. And then we have, so let's kind of look at this. So I have 2 electrons, 2 electrons, 6 electrons, 2 electrons, 2 electrons, 6 electrons. Where have we heard those numbers? Maybe have you orbitals? Exactly. What do we know about s orbitals? How many electrons can go in the s orbital?
2,
How many can go in the p?
6,
6. These
10.
and the s, if we ever did crazy enough to look at those, it would be 14. This is the evidence that was helping to support the orbitals and showing the electron configuration. So this is how you can write electron configurations. That's a common question. They'll give you this and they'll say, what's the element? So one thing to be careful with, and I think they've gotten consistently, look at the energy, look at the scale. Because this sometimes gets us. Is this starting at 0 here? This is actually your highest energy. So here are your highest, these take the most energy to remove. So are these electrons going to be closest to the nucleus or furthest away? Are they inner shell electrons or are they valence electrons? Inner shell electrons. So this is the valence electrons. These are the ones that get removed first. Now, that makes sense. It only takes 0.74 energy to remove a valence electron from magnesium. That's pretty easy. That's why magnesium is going to lose electrons. That's why metals lose electrons. So you can write configuration from a PES diagram. So this is 1s2, 2s2, 2p6, 3s2. So you just start with the highest energy and you can get a configuration from a PES diagram. So on the periodic table, when you're the orbitals, you remember this? Then, but using the periodic table, my S block, the P block, the D block, and the F, so they correspond to each other. So that's why you can have a PES diagram, and they can ask you, what is this element? You can have a PES diagram, and it can say, write the configuration. They can give you a PES diagram and say, oh, what's the valence ionization energy? You're just looking at the bottom. How much energy to remove that electron? So that's the PES diagrams. Don't freak out. Just recognize that they're just giving us the ionization. So these are the trends that they want you to know. Ionization energy, atomic and ionic radius, electronegativity, and then ionic charges, which means they all have group 1s, but also the size of ions. Compare those. So the why. Like I said, not buzzwords, but sometimes they're buzzwords. If you're talking about down a group, to me the groups make that they're easier because you can visualize it. As you go down a group, think about where are those valence electrons as you go down a group. Lithium is in what group? 2s1 is its valence electron. Sodium, 3s1 is its valence electron. Potassium, 4s1. So when you write configuration, what's the number in front mean?
It's which row?
Yeah, because when we write 1s2, 2s2, what does this number mean?
The row.
It's not technically the row.
Energy shell.
It's the energy level. The reason it's not technically, where's 3D?
Oh, because it jumps back right
Yeah,
there.
3D, remember, is on the 4th energy level. So 3D, so that's why it's not the period. But so what's happening as you go down a group? Where are those electrons going in reference to the nucleus and in their distance to the nucleus? Are they getting closer, further, staying the same? They're getting further away. Think of it like floors on an elevator. First floor, second floor, third floor, fourth floor. So if you're staying on the fourth floor, are you further from the lobby? And so look at Coulomb's law now. If you are dividing it by a larger distance, because that's the attraction, remember it's between the protons and electrons, if that distance is getting bigger, what's happening to that force of attraction between the electron and the proton? It's getting smaller. That's why the atoms get bigger. Well, plus you're adding more stuff. But that's why ionization energy decreases as you go down a group. Because it takes less energy to remove that electron because it has a weaker force of attraction. Because the electrons are further away. So this trend explains, or that reason explains all the trends. Why does electronegativity decrease? Because the electrons are further from the nucleus. So there's a greater distance, which means a weaker attraction. So therefore, it has a lower electronegativity, which remembers the ability to share electrons. Who can attract the electrons? Who shares electrons, steals electrons the most? In the periodic table, the trend. Huh? The halogens. And which of the halogens wins? And we put sometimes personalities on electrons, never say this on an AP test. We call fluorine the floozy. She steals everybody's electrons. But just remember, fluorine is the highest electronegative. It will still erase electrons. And it has the highest electron affinity and the highest electronegativity. So when you're looking at trends, everything gets greater going to there. So electronegativity is how well do they share. Okay. To me, the period trend is the one that doesn't make as much sense in the beginning. Because as you go across the period, are those electrons getting further away? If we could draw this. So we have 1s2, we'd have like 2s2. 2s1, 2s2, 2p1, 2p2, 2p3, 2p4. As you go across the period, they're going into the same energy level. So I'm not going to talk about distance when you go across the period. But what happens, you don't have any more core electrons. That effective nuclear charge, there's the word to talk about if it's a periodic trend. The effective nuclear charge increases as you go across the period. So therefore, they get smaller as you go across the period. Therefore, the ionization energy increases as you go across the period. So going across the period, you talk about the effective nuclear charge. So look at on this. This is how questions are going to show up. And I think I have on 2018 also. Find beryllium and boron on, so if we look at trends, that's a periodic table, by the way. Some of my kids call it a castle, periodic table. Where's the largest atom?
Down on the bottom left.
It's the biggest, that's the smallest. Where do I have the lowest ionization energy? Okay, the bigger the atom, the lower the ionization energy. So this is my highest. Okay, then for electronegativity, we know fluorine is the highest. Noble gases aren't part of that trend because they don't make compounds typically. And so fluorine has the highest electronegativity. Okay, but that's not going to get you the points of a Y. But that's a starting place. So we know ionization energy increases as you go across the period. We know that's what we've memorized in pre-AP. Okay, look at beryllium and boron. So they're saying the ionization energy, the energy needed to remove an electron, and we talk valence electrons, is 0.09 for beryllium. For boron, it's 0.08. Is that increasing? There's two exceptions they can show you and ask you to explain. In pre-AP, I always told mine, don't worry about the exceptions. Don't worry about the exceptions. You're not pre-AP anymore. We get to worry about the exceptions. What could be a possible reason that that happens? And they're not going to ask you to memorize all the exceptions, but they could give you this and ask you to explain the exception. What could be a possible reason that Beryllium and boron, you actually see boron decreasing. Okay, expand on that.
Whenever you're taking the next one from boron, you're switching to the p orbital.
Okay, because beryllium is 2s2, 1s2, 2s2, 2p1. Okay, what I would just do, you don't know why, it's not asking why, I would just say it just takes less energy to remove it from a 2p than from a 2s. The valence electron in boron is in a 2p. It requires less energy to remove a 2p electron than a 2s. That's all that you need to say. So find the reasoning. So that's one of the common exceptions. Here's the other common exception they're going to ask you. This is nitrogen and oxygen. Again, they're right by each other on the period, right? Nitrogen has an ionization energy of 1.4. Oxygen's ionization energy is 1.31. It didn't get bigger, it got smaller. Why? What is a possible reason? What is going on in that structure that could explain that trend?
Oxygen has an electron pair with another.
Okay, think about orbital diagrams, very good. If we drew nitrogen, that would be nitrogen in the 2p. If we draw 2p for oxygen, they start pairing up. What's the charge of electrons?
Negative.
Negative. Do negatives like each other? So there's a little bit of electron pair repulsion. And so since there's a little bit of electron pair repulsion, it's actually pushing it away a little bit. So since it's being pushed away a little bit, it doesn't take as much energy to remove it because of the electron pair repulsion. Again, that's those are the only two exceptions they're going to kind of ask for you to talk about. Okay, so before the NIMSY super problem, let's look at 2018. Again, I know we looked at it on thermochemistry. This time I believe it was question number, so this you could Google it. I believe it was question number, last question. There it is, look at what showed up. So this was on the free response portion. First thing I would do when you see these, look at the scale. So here is my highest, because there's different things they could ask you. They could ask you, what's the energy of a core electron? So if they ask you, what's the energy to remove a core electron, where would you look? Yeah, this is the core electron. Where do you look for valence electrons, or where are they going to remove electrons first? Right here. Okay, but look at what they asked. On A, you've got 1 point if you just identified this element. So what element is this? So we know this is what peak? 1s2. You're just doing configuration. So this is a 1s2. This is what? 2s2. And so each line must be 1 electron. So if we have 1s2, 2s2, this must be a 2p what? 3. So what element is 2p3? That's nitrogen. Okay, that was nitrogen. Then it turned into a kinetics, which we haven't done. There was another question on here that actually had to do with atomic structure. Let's do the NIMSY super problem. I'll find that one. Yay. Okay. So on the NIMSY super problem. Okay. So looking on A, an atom of hydrogen, it has a wavelength. Gives you the wavelength, but what did it give the wavelength in? Nanometers. As electron transition from a higher energy back to the second, calculate the energy change. So what do I have to do to calculate energy change? What formula are you going to use? And you have your formula chart. Don't forget you have a formula chart. So what formula, let me look at this though. Does this actually have as both? It has as two discrete ones, right? Because if you look at atomic structure, it gives you two formulas. It says energy is Planck's constant times frequency. Speed of light is wavelength times frequency. But it gave me a wavelength. But can I rearrange this equation?
Yes.
Yeah, to solve speed of light over wavelength, and then plug that in. So I can do it in one step. Planck's constant times the speed of light over wavelength, that will calculate energy. They give you Planck's constant, they give you the speed of light, and on this one it does have 2.998. On mine, does yours have 3.0 or 2.998? Doesn't really matter. So this is just plugging in the numbers that you found. Now these, I would probably turn back. Speed of light. But wavelength, what does wavelength have to be in? Meters. Nanometers is, nano is 90. So I know I'm going to have to divide. There's your setup. Now, this is where I'd really be careful on these problems, that you're making sure you know how to use your scientific notation button on your calculator, so you don't mess up the order of operations. Unless you want to type out 33 zeros, which personally, yeah, I agree. No thanks. And that's where I was trying to use the calculator on the iPad, and it did that. It gave me one answer with 19 zeros. I was saying, seriously? And I can't change it to scientific notation. But I counted zeros. Okay, so this energy should have been, you should have gotten 4.09 times 10 to the negative 19 joules. Now, not that you can always count on this. Typically, though, with light, it's going to be in 100 nanometers. Energy, you have a negative 19 exponent. Frequency is a positive 14 exponent. So sometimes I look at my exponents in that question, does it make sense? Unfortunately, if they don't give you just visible light, that won't be true. Okay, look at B. A second emission line, so this is just showing those lines, has a wavelength of 434 nanometers as the electrons transition from a higher energy level back down. Would the energy associated with the 430 nanometer be less than, greater than, less than, or equal to the 486? Do you have to do any calculation here? You could. I mean, technically, couldn't we? But I don't want to. So what is the relationship between wavelength and energy? Is it a direct relationship or is it an inverse?
Inverse.
It's an inverse. We know that right there. So the smaller the wavelength is going to have more energy, so you would just say it's going to be greater than, because wavelengths with lower energy, with smaller wavelengths produce higher energy. There's one calculation that I want to look at. Okay, this is a good one I've seen before. Let's kind of look at these calculations. because something weird kind of happens in this. So on this one, is it hard to calculate frequency if they give me a wavelength? What formula do I know I'm going to use here? If I have these two formulas, it gives me frequency and I want speed of light. What are you going to use? I mean, not, excuse me, I have speed of light. It gave me wavelength and a watt's frequency. This is a plug and chug, as long as you remember that. So your frequency would just be the speed of light divided by your wavelength, but what does wavelength have to be in? Meters. So you calculate your frequency. Frequency is in hertz. Okay, that wasn't the tricky part. Okay, look at this one. D is the one I wanted to look at. Calculate the number of joules required to break the bond in a single molecule of hydrogen. How are you going to answer that? Because it seemed like we were using all these formulas, and then look what they did to us. They kind of threw us something else. Because can I use one of those formulas to answer this question? No. But what did they give me up here? The energy required to do what? Break the bond, but this is in what? 432 kilojoules per mole. This is where that mole and molecule come up. How many molecules do I have in a mole?
6.02.
6.02. This is where you would have to use that. Because remember, when I looked at this energy or this frequency, this was for the single molecule. This is for one electron. So that was just the dimensional analysis. That you're just saying 432 kilojoules. Use your units. Kilojoules per mole. Sometimes when you're stuck, play with numbers. I used to do this in college physics all the time. Didn't know what I was doing. I can play with numbers. So it told me that it wanted to know joules. So what am I going to first have to do with my kilojoules?
Convert them to 1,000.
Okay, I can do that because it gave me enough hints. And then the other hand, it gave me a mole, but it wants a molecule. So what do I know I'm going to have to do?
Change it to 6.02.
1 mole is 6.02 times 10 to the 23rd molecules. So is this number going to be really small? Yes. But remember, this 432 was to change 632 times 10 to the 23rd molecules. So I expect that this number is going to get 19 joules. And at first that looks random. But then look what they ask you to do in question set and E. There really was a purpose of that. And I remember this question was from a few years ago. They actually then wanted you to do this E. Where did it go? What are they wanting you to do in E? How many joules does it take? So, answer the question. How would you answer that question? What would you have to do to be able to answer that question? The problems disappeared on me, and that's where I was just trying to find it. Oh, I just went too far. That's what I did. Okay, so look at E. Does the photon have enough energy to break the bond? What are you going to have to calculate before you can answer that? What did you calculate up here in C? On C, you calculated the frequency of that photon. So if you know frequency, what can you calculate? Plug in your answer from C. So here's the energy that that photon at 300 nanometers, it has enough energy, 6.63 times 10 to the negative 19 joules. So this is for one photon at 300 nanometers, is what you just calculated. So it's asking, is this enough energy to break the molecule? So what are you going to answer? Is this bigger than this?
No.
No, so it doesn't have enough energy. But in AP, make sure that you complete the statement. That wouldn't give you the credit. You would have to say 6.63 times 10 to the negative 19. You could say in words. You could say is less than 7.18 times 10 to the negative 19 joules. Therefore, no, not enough energy. To break the bond. Just leaving answers isn't enough. You have to pull it together. Okay. That's the end of the math. Let's look at the concepts on these. Okay, they gave you hydrogen and oxygen. I don't like this question. But they didn't ask me when they wrote these. Using the evidence of the PES, explain why 2 atoms of hydrogen and 1 atom of oxygen are required to form water. What would you say to answer this? I know, I kind of agree with you. So I'm not a fan of this question. But we need to answer it. So what evidence could we say? To me, I'd go back to probably a pre-AP knowledge. What would you say?
When they both put together, it gives them both a full balance.
Okay, so tell me a little bit more because you're 100% there. So start with what they each have.
Hydrogen has 1 valence electron.
Okay.
It needs 2 for a full outer shell.
There you go.
So it needs 1 more on each board, and then oxygen needs 2 more electrons. So it just gives them 2 electrons.
So we know each hydrogen only has 1 peak of oxygen. The last of oxygen. So he's absolutely right. Oxygen needs 2, but each hydrogen only has 1 valence. So therefore, you're going to need 2 hydrogens to bond with every 1 oxygen. I don't feel like that's really showing it. I feel like that was a stretch to get the PDS diagram. But this, I've seen this question. Okay, look at G. Circle the peak that contains the first electron that would be removed from an oxygen atom. You literally get a point for circling a peak. Which peak in oxygen would you circle? Okay, the far right. That's all you'd have to do. Circle that 1.31. And then, what's the value for the ionization energy? 1.31. 1.31 megajoules per mole. They just want to know you know what this thing is telling you. I know, guys, we're getting tired. I'm getting tired. I'm trying to find. Okay, last thing I want you to be able to explain. We didn't look at ion sizing. between just the nitrogens, we're just looking at these right now. Between these, which one's bigger?
The -3? Wouldn't
Wait, the one with.
This is another common type question, so it really wasn't in the packet, so let's talk about it more.
The one on the right because it has extra electrons.
Yeah.
There you go.
Duh.
Okay. If they ask this type of question, they ask you to compare two things, protons and electrons. So both of these only have 7 protons. But how many electrons in here? 7, but how many in here? 10. So this has the same number of protons. Okay, now there's more electrons. Now this is what you need to talk about though when you have more electrons. It's back to the reasoning. What do those electrons, what do they start doing?
Repelling?
They start repelling. So there's actually more electron pair repulsion in this one. Therefore, that's why this is bigger. What about, what if I have O-2 neon and I have sodium? Which one in here do you expect to be bigger? Let's say it's smaller. Let's say it's smaller this time.
Smaller?
Smaller.
Wait.
Sodium. No?
Okay? Which of these is going to be smaller?
Yeah.
Okay? Okay, here's a word for these. These are all isoelectronic. So if you ever see the word isoelectronic, iso means the same. They have the same number of electrons. Look at what's different here. 10 electrons, 10 electrons, 10 electrons. Okay? But how many protons in here? How many protons in here? How many protons in here? Protons are the pulling power. These have more protons, so therefore this you expect to have a stronger attraction. This is actually going to be the smallest. Okay? So if you have the same number of protons, talk about the electrons being different. And the electrons, the more electrons you add in there, you're going to get more repulsion. If the electrons are the same, then you talk about the protons being different, and the protons have a stronger effective nuclear charge. That's what's going to be the difference in the size. And they've gotten really specific, saying you need to talk about both. So just even writing out, they both have the same number of protons. However, nitrogen only has 7 electrons, and nitride has 10 electrons. Therefore, there's greater electron repulsion in this, and it will be larger. Something like this. They all have the same number of electrons. However, oxygen only has 8 protons, neon has 10 protons, sodium has 11 protons. Therefore, sodium has a stronger attraction, and it will be smaller. Can we use bullets when we answer questions in chemistry?
Yes.
We can. Don't do that in AP Bio or AP Environmental. They want words, more words. You could use bullets. But you still have to connect the thoughts and connect your dots through that. Try to find a good question. Something that's not actually. Okay, let's look at C on I think this is on the very last page in your packet. Let's practice one last explaining. The why, because that's part of it, it's the justify, justify, justify. The one that said modified for a short response. Do they have page page numbers this year? No, of course not.
Yeah, it's the very last page.
Okay,
That's the very last.
yeah. Okay, so this is on the very last page. Okay, so you should find, first thing, find the periodic table and find what these have in common with each other. First thing to talk about. So, selenium and bromine, how are they related? Is it a period trend or is it a group trend? Okay, they're the same period, right? Selenium is right there at 4p, 4p4. Bromine is a 4p5. Okay. So why is bromine higher ionization energy?
It is further that way.
Okay. Just saying it's furthest right, closest to a noble gas isn't going to get a point. Okay, that's memorizing arrows. They don't want you to memorize arrows. So across the period, so you really, remember in your trends, you have two things you can talk about. Going down a group, you talk about, and it's all about Coulomb's law. Okay, if they're asking to explain a trend, you should think Coulomb's law. Think Coulomb's law. So there's two things you can talk about in Coulomb's law, the charge or the distance. And the charge they're talking about specifically in trends is the effective nuclear charge, which is total number of protons minus 4 electrons. It's the same as the valence electrons. +1, +2, it increases. So if you're talking about a period, are you going to talk, is there really any distance change between the nucleus and the valence electrons? Because there was 2p4, 2p5, or 4p4, 4p5. They're the same energy level, so don't talk about distance. So across the period, the distance is the same. So if the reasoning has nothing to do with distance, then what are you going to talk about?
Charges.
The charges, specifically the effective charge. Selenium has 1 less proton than bromine. We even told you bromine has the 35, but this has an effective nuclear charge of +6 versus +7. You don't even need to know the numbers. Just say selenium has a weaker effective nuclear charge, therefore there is a weaker attraction, and it takes less energy to remove an electron from selenium compared to bromine.
The following students please report to the labo table. Nicholas Wagasak, Shamaria Hughes, Reagan Sunday, Caitlin Couillon, Ella Atkins, Sarah Collins.
Did we get a winner?
Jacob